We have several videos with a discussion of the metabolism of lipids, but in this video, I want to go through the mechanism of how are the coenzymes participating getting reduced. We discussed in the oxidation of a fatty acid that the process will include two oxidations, one hydration, and the cleavage between the alpha and beta carbon. FAD and NAD plus are electron carriers, and coenzyme A is a carbon carrier. Flavin adenine dinucleotide, FAD, is a common oxidizing agent in catabolic reactions. It is reduced by the formation of covalent bonds with two hydrogen atoms to give what we call FADH2. Besides its action in the lipids metabolism, we will find FAD also in the citric acid cycle. This coenzyme has three important parts: the ADP part, the ribitol part, and the flavin. It is in the flavin where we will take 2 electrons and 2 protons. Nicotinamide dinucleotide will enter the active site of enzymes where redox reactions are needed. The reduction of NAD plus occurs by addition of a hydride ion to the ring in the nicotinamide part. In both molecules, FAD and NAD plus, the ADP part works as a handle by which the apoenzyme holds to the coenzyme. The positive charge on the nitrogen works as an electron acceptor. The last component necessary for the beta oxidation of lipids is the acetyl carrier coenzyme A, and this one is also made of one ADP part, a pantothenic acid, and the most important part is the aminoethane thiol, which is the part that is going to make a thioester bond with the carbonyl that will carry. Also important that the ADP part is modified because it has a phosphate unit on the carbon number 3' of the ribose. I have done a video about the beta oxidation of fatty acids, but in here I will do just a little overview of the steps, and the steps are: the first step is an oxidation. We are going to oxidize between carbon number 2 and 3 to form an alpha-beta unsaturated thioester. Then we're going to do a hydration. We're going to add a molecule of water where the OH will be added to the beta carbon. Then we're going to do a second oxidation to produce a beta ketothioester. And the last step is the thiolysis, in which we're going to cleave between the alpha and beta carbon, releasing a 2 carbon units molecule of acetyl coenzyme A. On the first oxidation, we will use the coenzyme of FAD, and on the second oxidation, we're going to use NAD+. Also, we're going to use coenzyme A on the very last step to cleave 2 carbon units molecule that can produce acetyl coenzyme A that is then available for the citric acid cycle. The cycle then starts again with a remaining acyl-CoA, which is now 2 carbon atoms shorter. At each turn of the cycle, 1 acetyl-CoA is produced. Since this fatty acid has 12 carbons, it will turn on this pathway 5 times to produce 6 units of acetyl coenzyme A. The beta oxidation of fatty acids involves the chemistry of the alpha carbon. In order for FAD to be reduced to FADH2, an amino acid from the enzyme removes a proton at an alpha carbon and transfers a hydride ion equivalent from a beta carbon to FAD. Deprotonation of an alpha hydrogen by a basic group such as a glutamate or an aspartate will trigger the formation of a carbon-carbon double bond when the hydride ion of the beta carbon adds to nitrogen number 5 on the flavin ring, while an acidic amino acid side chain protonates nitrogen number 1. pay close attention to the push of electrons. The products of the reaction are FADH2 and the trans-alpha-beta unsaturated thioester. The oxidation of the secondary alcohol on the beta carbon of the fatty acid will take place by the reduction of NAD+ to NADH. The substrate that is being oxidized by NAD+ donates a hydride ion to the fourth position of the pyridine ring. This will happen after a basic amino acid side chain deprotonates the alcohol part of the fatty acid. In the reaction, first the basic amino acid removes a proton from the alcohol part. That will produce the carbonyl of the beta-keto-thioester, kicking off a hydride ion that adds to position number 4 on the pyridine ring. This is possible because the nitrogen with a plus charge is an excellent electron acceptor that we call an electron sink. We end with the beta-keto-thioester, NADH, and also always a proton is extracted from the metabolite to the solvent. The thiolase reaction occurs via a Claisen ester cleavage. The active site of thiolase will have an important cysteine amino acid, an important aspartate, and coenzyme A. Cysteine will become better nucleophile as a sulfide after an acid-base reaction with the aspartate amino acid. The sulfide formed from the thiol group of cysteine will add to the beta-keto group of the substrate acyl coenzyme A. Upon this addition, we will form a tetrahedral intermediate of ethiohemiacetal. When the tetrahedral collapses, it's going to form an enolate, and the rest of the fatty acid will make a thioester bond with the active site of the enzyme. The enolate is very stable due to the contribution of two resonance structures. To release the 2 carbon units of acetyl coenzyme A, the enolate is protonated by the aspartate from the active site. This product can enter the citric acid cycle if the energy charge is low. To release the fatty acid from the active site of this enzyme, we will use coenzyme A. After the nucleophilic attack of the thiol group to the thioester, we will have the formation of an intermediate tetrahedral that when it collapses, it will form a thioester bond with coenzyme A. We will get 2 products, the fatty acid that is shortened by 2 carbons and acetyl coenzyme A that can enter the citric acid cycle.